Oh, I got it now.
Okay, so now we're on the way. Thank you for helping each other remember. Thank you, Diana. For helping those around you remember that to find the x of the vertex, we're going to do negative b over 2a. So in this case, we get negative 2 over 2 times 1. So the x of the vertex is negative 1. Now how do we find the y at the vertex?
Plug it in.
Plug it in. All right, so we're evaluating the function f for a value of negative 1. And when we plug in that negative 1, we're going to square it. And then we're going to multiply it by negative 2. And then we're going to subtract 3 from that. And the value of the function when x is negative 1 is negative 4. So that tells us that our vertex is located at the point negative 1, negative 4. And if I ask you to write it in vertex form, you could, because we know a is the same.
Yes.
So there's nothing out in front. So it becomes x plus 1 squared minus 4. So we're going to go over to negative 1, down 4. We're going to go up. A is 1, so we have normal. A over 1. 1 squared is 1. Left 1. Negative 1 squared is 1. Right 2. 2 squared is 4. Left 2. 2 squared is 4. And then to the best of your ability, you would draw in the problem. Vertex form is f of x is equal to a times x minus h plus k, where our vertex is hk.
Oh, I see.
So that minus the negative made a positive.
Understood.
Okay? All right, so this is what we've learned so far. But obviously there was a reason why we took a time out from what we were doing and learned how to factor. So, if I ignore the f of x and the equals, this is a trinomial. Will this trinomial factor?
Yes.
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 Okay, so this factors to x plus 3, x minus 1. Now, we can see from the graph that the zeros of the function are, which is what I should have ended up answering to start with. The zeros of this function, we can tell from the graph we just made, are negative 3 and 1.
Wait, but why is it opposite?
Okay, so let's talk about why it is the opposite. When we ask for the zeros of the function, it's because the y value is 0. What is the only way to take a product and have that product equal 0?
Multiplied by itself.
Is if this were 0 or this factor equals 0. If either of these factors were 0, would the product be 0?
Yes.
Okay, so what would make this factor 0? Negative 3. And what would make this factor 0? 1. So my zeros of the function occur where x is negative 3 and x is positive 1.
That was not so bad.
How do you
You had this pre-planned.
Okay?
Just to mess
On
with it,
purpose.
didn't you?
Yep, I did. Okay, so let's go back and say, let's say I didn't do any of this, and I just did this. Could I graph it?
Yeah.
I could, because I know that a quadratic is a symmetric function. So the axis of symmetry would have to be halfway in between these 2 points, wouldn't it?
Yes.
Which would locate that axis of symmetry right here at x equals negative 1. Is that what I found a minute ago that x would have to equal?
Yes.
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 So it's halfway in between. Halfway in between is just averaging, right? So if you can't just look at it and tell halfway, you can add them up and divide by 2. And we still get negative 1. So now that I have the x, I can look at this 2 ways. I could plug it back in to find my y. Or I could go, oh, this is a squaring function. If I moved 2 away, what is 2 squared? 4. Is this to open up? I'm going to have to take this vertex down.
This is so
4.
satisfying.
Isn't it awesome? Awesome. Yes, ma'am.
Is it always going to be where, like,
Yeah. Eric.
like on that line?
Eric. That's
Or-
the point of this.
The zeros are always going to be located on the x-axis but they're going to be different distance from your axis of symmetry. We're going to do lots of examples so you can see lots of different ones. Okay, so I could fill in the other points if I wanted to, because I know there's no multiplier here. That's an understood 1. So I know my moves are normal. And there's that way to graph it. Okay, so the first time we see something, it usually doesn't completely sink in. So let's do another one. All right, so here's a new function, still named it f of x. But f of x is equal to x squared minus 8x plus 12. So let's take this one and look at it from the factoring standpoint. Will this part of the function factor?
Yeah.
Yes. What does it factor to?
X minus 6, X minus 6.
Good. X minus 6 and x minus 2. So if either of these factors equals 0, then the product would be 0. So what can I plug in here to make that factor equal 0? 6. Or what can I plug in here? 2. So I know my x-intercepts are located at 2 and at 6. So the axis of symmetry would be located at x equals what?
1.
4. What's halfway in between 2 and 6? 4. Woo, I missed it totally, but you got it. Okay, there we go.
I don't even somewhere. Okay.
Okay, now this time once again, these zeros are located how far away? 2 units, and 2 squared is 4, so we're still down here. We're going to do one in a minute that's different. See, there's my function.
Is it like time splitting when it's not 2 away or something?
No, we just, like, if it's 3 away, we would go up or down 9, because 3 squared is 9.
Yeah.
Unless there was a leading coefficient. Like our next example.
Okay.
Okay, so let's look at our next example. Example 3. This time we have the function g. So g of x is equal to 3x squared plus 12x. Okay, this one factors differently because it has a GCF.
Yes.
What is the GCF? 3x.
3.
So we have to factor out the 3x. And so what is my other factor?
X plus 4.
X plus 4. Okay, so do you see I have the 2 factors? 3x is a factor, x plus 4 is a factor. So, what can I plug in here that would make that first factor equal 0? 0. What can I plug in here that would make the second factor equal 0? Negative 4. Okay, a lot of you got this one right off the bat, but I'm going to go back to it for a second because some of you are going, where did they get 0? All right? When we just factor out an x, if we plug in 0 for that, we're not adding or subtracting anything to it. So that's why if I plug in 0, it makes that factor 0. Okay? So we're going to come over here, we're going to graph it. We're going to put 1, 0 here, and we're going to put 1. Okay, so those are my zeros of the function which occur at the x-intercept. So that's why I plotted an x-intercept at 0, 0, and another x-intercept at negative 4, 0. Okay, and this one is still going to be 2 units away from the axis of symmetry, isn't it?
Yeah.
But this one has a 3. So what happens to those moves? They are multiplied by 3. So instead of going 2, 4, I'm going to go 2, 12. So my vertex is not on the graph, you're right. I know that's why you don't like it. It's located at the point negative 2, negative 12. So it's real skinny.
Well, where'd you get the negative 12 from?
Okay. This is 2 units apart, and so 2 squared is 4. But because of the vertical stretch by a factor of 3, we have to triple that 4, and that's where it turned into 12.
That's not this.
Okay. I like this last one totally. It has lots of fun stuff. Oh, it looks scary, but it's about to turn into something that's not scary at all.
Really? See a lot of
Okay.
I blame you.
You see a lot of threes, don't you?
On the bottom.
And on the bottom, and you don't like that.
No.
Okay, the other thing that I see a leading coefficient that's negative. And I kept pounding on the fact that, you know, when we see negatives, we want to factor them out because of what we're going to do next. We're there. We want to factor out that negative, and we're going to factor out a negative 1/3. And watch really cool things happen. If we factor out a negative 1/3, am I just left with an x squared?
Yeah.
Am I left with a 4x, but it's negative because I factored out a negative 1/3 and a negative 5.
Yes.
Oh, isn't that much nicer?
Yes.
Yeah, it is much nicer.
Yeah.
Okay, so after I factor out the negative 1/3, this trinomial factors really nicely.
It's gonna be
X minus 5 and x plus 1. Good.
Okay.
So, what would make this factor equal to 0? 5. So I have an x-intercept of 5. That's one of the zeros of the function. What would make this factor equal to 0? Negative 1. So I have another x-intercept at negative 1. That is also a 0 of the function. My axis of symmetry would have to be halfway in between. So sometimes when we throw in the negative numbers, it's harder for us to visualize it, but negative 1 plus 5 is 4, divided by 2 is 2. When you draw it, you see it, 2. Okay, now I can't just get jumping on these things. I've still got to use what I learned about quadratics. This tells me this one's opening down, doesn't it? This negative 1/3 tells me it's opening down. So this time, instead of going down to get my vertex, I have to go up. Now, this time, my zeros are located 3 units away. Then 3 squared is 9. But there's a vertical compression by a factor of 1/3. So what is a third of 9?
3.
3. So it's right there.
50.
And there we go. Okay, you try 5 and 6. You don't have to graph it, but see if you can find the zeros of those functions. Just find the zeros. Okay. I saw great things when I was walking around. You guys factored this to x minus 6 times x plus 1. And so you determine the x-intercepts of this function occur at 6 and negative 1, so those are our zeros. The zeros of the function are where x has a value of 6 or negative 1. Yes, I am.
I didn't even know.
Okay, now this one just has the GCF, and sometimes just having the GCF throws us. We always want it to do more, but sometimes it doesn't.
Yeah.
So x would be 0 or 8. So those are the zeros of our function. The zeros of our function are 0 and 8. And the x-intercepts occur at 0 and 8. Now, I'm going to show you something. It's extra. I'm not even going to charge you. Okay?
Can we charge you?
Alright. So let's say I took a polynomial function and I factored it over the set of integers and it factored to this. Now everything we've done so far has not had a leading coefficient, but they certainly could. If we were to look at this and we were to go, okay, if this were to equal zeros, for some of you it may not be as easy to just look at this and see, so you may have to go, oh, let's set it equals 0, and then I'm going to move that 5 over, and then I'm going to divide by 2. But some of you may remember from graphing linear functions that we can find the x-intercept by doing, do you guys remember this form, ax plus b? And set it equal to 0, you move that over and you get ax equals negative b. So to find the x, you just do the opposite of b over a. If I did the opposite of this over that, is that what I got?
Yeah.
Okay, so this one would be positive 2 over 3. Okay? And that's how we get those. Alright. Now this one. This says to find the roots. Okay, I've been talking zeros. We've been talking zeros. But we were also looking at functions. Now we're looking at an equation. And they've switched the name on us from zeros to roots. So when we talk about the roots of an equation, we're talking about the solutions when we solve that equation. We're going to solve the first one by factoring. So to solve by factoring, step 1 is to set the equation equal to 0. And then step 2 would be to factor. Okay, so this first equation is really simple to set equal to 0. We just have to move the 1 over. And everybody gets excited because they're like, whoop, easy, difference of squares.
Yeah.
Yep.
I was so excited.
I saw the excitement. That's why I said it like that.
Why would you set the 1 over?
Okay, because that's, to solve it, we want it to be equal to 0, so we can use that same thing we've been doing by going, if the product equals 0, then either this factor has to be 0, or that factor has to be 0. So what can I plug in here to make that first factor equal 0?
Negative 1/3.
Negative 1/3. Negative b over a. Or positive 1/3. Okay, now, somebody in here worked ahead. Go ahead. Own up to it. Somebody worked ahead and did this problem. Who did it? Nobody?
You think we're a lot
Okay.
more proactive than we are.
Nobody's owned it up to it. If you worked ahead, this is probably what you did. You went, oh, divide by 9. X squared equals 1/9. Square root, plus or minus. X equals plus or minus 1/3. Oh, you see we got the same answer?
Uh-huh.
Okay, now, this one, you didn't have to factor to solve it, did you? You could have just taken the square root of both sides. And when there's an easier method of doing something, choose it. Unless I've stood up here and stomped my foot and said, I want you to do it this way, which I don't do very often. And when I do, it's because I know what's coming next, and I know it's important for that. But if there's multiple ways of solving something, choose the easiest correct method. Now, you can't make up math that doesn't work and solve stuff. But always go with the easiest one. This one, I would just take the square root of both sides. Be done with it. Now this one, would that work for? Could I just take the square root of both sides for this one?
No.
No. This one has a linear term. So you're going to have to factor this one. So to factor this one, what do we do first?
Set it equal to 0.
Set it equal to 0. So we're going to move that 40 over. And then when I move it over, I'm going to put it in the right position. Okay, what always step 1 when factoring? Greatest common factor, GCF. What is the GCF of this polynomial expression? 2.
I don't have a calculator charger. Mine's dead. I hear you.
Okay, that worked nicely. Because what did it create right here? Perfect square. Perfect square trinomial that will factor to a binomial squared. So what does it factor to? 2x minus 5. Quantity squared. There are a lot of 2's.
There's too many twos.
Okay, there's so many I'm going to get rid of 1.
Okay.
Okay? I'm going to divide this side by 2. And whatever I do to one side of an equation, I must also do to the other, right?
Yep.
So this 2 just went away. Which is totally fair in this case. Now, if this were a y equals, we couldn't just make that 2 go away. Because that 2 would represent a vertical stretch, wouldn't it? That 2 would be important. But this isn't a function, it's just an equation. So that 2 can be divided out, and we don't have to worry about it. It's gone. But if it were a function, we couldn't just get rid of it. It would have an importance. Yes, sir?
Instead of doing that, could we just leave it the
You
original?
could. Sure. You could just leave it, because there's no way to turn that into 0. So this is the only factor that you could rewrite as 0. And so what can x be? 5 halves. Now, if it had been a function and not just an equation, what would that 5 halves represent?
The y.
It's an x-intercept, isn't it?
Yeah.
But how many do I have?
1.
One of them. I just have 1 point at 5 halves, don't I? So that is also the vertex.
Ah.
And it would open up. Okay? So we would call this not just a root, but a double root. And the reason we call it double is because of
2.
the 2. And watch this. Whether I approach from the left, I get that point, or from the right, I get that point. From either side, it's a double root. Either way I approach, I hit that 1. It's considered a double root. So we're going to look at multiplicities, that means multiples, at roots as we get into the higher degree functions. We see what happens on a quadratic when it has a double root. That's where our vertex is. We're going to see what happens with a cubic when there's a double root, or a quartic. Could be a triple root. Yes, Ben had his hand up first. Okay.
Wouldn't you get a different answer if you hadn't divided out the 2's?
Nope.
The only reason I say that is like, isn't it when you have a 0, wouldn't the 0 make the 2 0, like if you're trying to find the x-intercepts?
If we have turned this into 0, does it matter if the 2 is there or not? Because 0 times anything is
Oh yeah.
0. Okay,
I got it.
Okay, cool. You
Makes
asked me the
sense, Miss
question.
Willoughby.
Good. All right. The last thing we're going to look at is application. And we talked about this a little bit, but today we're going to look at it intensively. Here we go. An object is thrown or launched into the air, such as a baseball, or a basketball, or a soccer ball, or a rocket. When we launch those things, we call them projectiles. Okay? So our general function that approximates the height in feet of a projectile on Earth after t seconds is given below. Now, this is on Earth because this first coefficient is a constant that represents the Earth's gravity. So if we went somewhere else, we have a different pull of gravity, wouldn't we? So this negative 15 feet per second is the effect of the pulling of gravity on objects on Earth. Make sense? Now, if you were in science class, you won't see the negative 16. You'll see negative 4.9. Because in there, you work in the metric system, correct? So that would be negative 4.9. That would be meters per second.
Did you just
And here,
Did you just do that, or did you already know that?
I know a little bit about things that have to do with math and science.
I mean, like, did you just calculate?
Well, I learned in high school about, and I just remembered. It's always that. It's a constant. It's always this number. It's always that number. Now, the ones that can change are highlighted.
It's so constant.
V naught. V naught. Everyone say that with me. V naught.
V naught.
Good. That represents the velocity of the object at time 0. What is the initial? V naught means at time 0. So the initial velocity of the object. And it's talking about a vertical velocity, the initial velocity going up because we're launching, right? All right, and H naught represents the initial height. And this could change. If we're talking soccer ball, it's probably on the ground and we're kicking it. So the initial height, most of the time, is 0. Now, occasionally we get to pick and throw, don't we? So we've changed the initial height. Okay? And it's from wherever we are. I don't really play soccer. I've watched it. It looks like a very interesting yet boring sport all at once. I think if you're playing, it's got to be awesome.
That's how baseball is for me. Like,
Yeah, I know.
I can't watch it.
I know it's awesome. Okay. So, some of you are already thinking, and I love it when you do think. Now, this model does have limitations, and it notes them here for you. Some of the limitations, obviously not all of them.
Yeah.
But this model, mathematical model, is not accounting for air resistance.
No.
It's not accounting for wind. It's not accounting for other real-world factors that might affect. But it's a pretty good model because
It's not real world.
sometimes we have to go pretty high for the wind to matter. We hit a line drive in baseball, it's not going to be affected by the wind so much versus if we hit one that goes up. Anyway, so this is a good model for us. Now, number 9. A soccer ball is kicked from ground level. If it's kicked from ground level, what's the initial height? 0. So our H naught is 0 feet off the ground. With an initial vertical velocity of 32 feet per second. So V naught is 32 feet per second. And how many seconds, so we're looking for time, will the ball hit the ground? If we're back on the ground, what is the final height at the end of the time? 0. Right? So if we plug in what we know, my final height is 0. The effect of gravity doesn't change. My initial velocity was 32 feet per second. And my initial height was 0. So here I am. I've got the ball. Who plays soccer in here? Okay, lots of people play soccer in here. So one of you has kicked the ball. And it's going to go up, and then it's going to come back down. Okay? It doesn't do like that. It follows an up-down parabolic path. So, now this is actually just reflective of the height of the ball, not really the path of the ball, even though I drew it like it's the path of the ball. So what is this time? What is this time right here when it hits the ground again?
0.
So the first time that it's on the ground is time 0, because we start off on the ground, right? But do you see if we factor this? Do you see it has a negative 16t GCF? And that leaves me with t minus 2. This first time would be 0, and the second time is 2, which means when it hits the ground, that occurs 2 seconds later.
Wait, where'd you get the T minus 2 from?
I factored out the GCF,
Oh, okay.
which was negative 16, and when I did, it left me T minus 2 as one of my factors. So what I could plug in for T here to make this factor 0 is 2. Okay, take just a minute and see if you can do number 10.
Use this.
I was talking about that.
Oh, are y'all gonna?
Yeah, we're about to.
Yeah.
Yeah, we should.
They're gonna have to throw down.
Yeah.
Yes, sir. Wait. No. Yes, it would. Yes.
I think I got it.
Oh, wow. That one was fucking so dumb.
Okay, any questions? Okay, now sometimes they actually give you the model. They don't ask you to create it. Sometimes you're given a model that represents a situation. So it may not be a projectile object height with respect to time. That one, I would expect you to know. I'm not going to give you the equation. I want you to know this one. Because this is actually a very good real-world application of mathematics. Okay, your homework is out of the workbook, and I want you to get started on that while I finish grading the quizzes. And hopefully I can get this back to you with a few minutes left in class.
Or just don't get that ball, you know what